Welcome to video number 2. So this is part 2 of 8.1 equations of lines in R2 and R3. That's 2D and 3D. I'm going to go about trying to explain this because it's the same concept. I'm going to try to explain it by introducing two different ways of describing a line other than what you already know. So as a recap, you should be familiar with vertex form. That is a position vector and a direction vector. You should also be comfortable with parametric form. That is, in a line, the x and y are defined by a equation of sorts with a parameter, okay, with the same number, right? I am going to show you that a vector equation can also be written in something called a scalar form. A scalar equation, and it looks something like this, literally an x and a y and a number. And also something that's subtly hidden called a symmetric equation form using our knowledge of parameters. That sounds a little bit weird, so let's go through what we know in this question. Okay, day 2. Consider this line in parametric form. Should I write that? So this, as a reminder, parametric form. Find the coordinates of 2 points on the line, any 2 points. So, okay, the easiest points I can give you is setting t equals a 0 and maybe setting t equals a 1. So if t equals a 0, x is 3 plus 0, and y is negative 5 plus 0. Okay, so on the line, 3, negative 5 exists. And the same thing here, if t equals 1, we've got a 5 and a negative 1. 5, negative 1 exists on the line. Simple. Let's do B. Write a vector equation of the line. That involves us drawing information from parts of the parametric. That should be simple enough. The resultant vector is by first reaching 3, negative 5. I could also use this, by the way, if you remember. As long as we reach any point on the line, we can use our slope or our direction vector to get us anywhere else on the line. So it could have been this plus my direction vector of 2, 4 times t, where t belongs to any real number. Or you could have changed this to 5, negative 1, or any other point you have calculated on this. Like, let's say you use t equals 5 and you found some other point. You could have used that there too. Hope that makes sense. If not, put a little star next to that and say, Mr. Kim, what did you mean by that? Okay? Vector equation. C. This is the new part, so can we leave it last? Writing a scalar Cartesian equation, and in doing so, I'm also going to introduce symmetric form or symmetric equation form. Because sometimes this term pops up and it wasn't like formally taught in the textbook, I think. Determine if line 1 is coincident to line 2. Okay, so let's do that. If you want to check if this line 1 is coincident to line 2, that is just another extension of our previous question. How do you know if they're coincident? You can first check your slope or your direction vectors to see that they're going in the right direction. So let's try it. If this is the case, I need to check if my direction vector of 2, 4 from line 1 is a scalar multiple of the direction vector for line 2. And right off the bat, I don't see it because that's a 1 to 2 ratio. That's a 1 to 4 ratio, right? So let's just prove, is 2k possibly equal to 3? And is 4k going to equal to 12? Well, if I want k, I divide both sides by 2. And by sliding it over here, what do I get by multiplying the k value? I get a 6. That is not a 12. Therefore, L1 is not parallel to L2. Therefore, there's no way they could be coincident. is not coincident to L2. Okay, that's it. And so, basic questions. Now let's get to this thing called a scalar equation of a line. Remember, we are talking about this if it wasn't a vector. And I know you know how to do this. We're just simply taking our vector equation and trying to make sense of it in a scalar way without any vectors. Like if you notice, there's no vectors. There's no vectors in this equation, whereas all the other ones there were, right? So let's do it. Write the scalar equation of the line. We've got, this is brand new, so I'm just going to pretend it's a step-by-step instructional. Set up your x. Right? Set up your y. Okay. Notice, because of your parameter, we do not have any vectors. This is part of your vector, and that is part of your vector, but it also defines where you are on the line. I would like you to isolate for t. So I'm going to write right under here, isolate for t on both x and y. Okay. So for x, I'm going to subtract both sides by 3 and then divide by 2. So x minus 3 equals 2t, and so t is equal to x minus 3 over 2. Here, y plus 5 is equal to 4t. That means t is equal to y plus 5 over 4. Now, why am I doing this? Remember, all this time, every single time I said, hey, t is the same. T is the same. Whatever I have for here, I can slide over and try to find the y value. The parameter doesn't change for a specific xy coordinate. So here you can argue whatever my t is, it will be the same here. I can rewrite this. It's sort of like a substitution. I can write how x and y are related to each other as so. This right here, when you compare when you compare two different equations that equal the same parameter, this right here is what we call a symmetric equation form. It's useful in its own ways, and so it's going to pop up here and there, okay? But we need to go through the symmetric equation form to get to our scalar, and that is, I'm going to multiply both sides by 2 and 4, or rather get rid of the denominator. So watch this. Since 2 is a multiple, 4 is a multiple of 2, I'm going to multiply both sides by 4. This becomes 2x minus 6 equals y plus 5. If you're wondering what the heck did I just do, I multiplied both sides of the equal sign by 4. Try it out, and you'll get the same result. Next, I'm going to bring all of this to one side. We've got 2x minus 6. 1 second. Is it easier? Is it more confusing if I... Right. You know what? Let's not do that because I want to make a point of this. I'm going to multiply both sides by 4. Okay, just 4, which gets me 4x minus 12 over 2 equals y plus 5. Okay, and now I'm going to multiply both sides by 2. That gets me 4x minus 12 equals 2y plus 10. And then I will bring everything to one side, giving me 4x minus 2y minus 22 equals 0. Now, I know I could reduce it, and by all means, you could reduce it, but I actually wanted to make a point. Do you notice something interesting about this point and that? In other words, the coefficients of x and y, and my direction vector being 2 and 4. The change in x is a 2, the change in y is a 4. The coefficient of x is a 4, and the coefficient y is a -2. It's like the numbers were switched and one of the numbers became a negative. Does that ring a bell? I hope it might have. The concept that I want to deliver is that the numbers we see as a coefficient to the scalar equation is a negative reciprocal of the direction vector. Okay, that must be a handful. So first, let's establish what I have here is a scalar equation. You can find this by isolating, so taking the parametric equation, isolating for t, the parameter, and making the t disappear essentially by doing a substitution. You get yourself a scalar equation, and notice that there is no vector here. This scalar equation also represents our line. That's it. That's essentially the lesson, but there is also a very powerful tool in knowing how the coefficients of x and y relate to my direction vector. So even if you don't understand it, I just want you to adopt this idea. If we have a direction vector, the scalar equation will always have the coefficients as the normal. So let's say my slope was what was it? It was the direction vector was my direction vector was 2, 4. Right? My normal to that, if you remember from the previous video, would be the numbers are switched and one of them is a negative. So let me do, I don't know, let's do that one as negative. Okay? The equation of my scalar would end up being -4x, a +2y, plus something which we'll figure out later. But it's really, really powerful to know that the normal directly shows up in the scalar equation. I'm going to show you some examples of that. Okay, so for this video alone, that's all I want you to adopt as something new. Your parametric or your vector equation can be written as a symmetric equation. It can also be written as a scalar equation, and they all have their special unique uses. Okay, let me show you how how it's done, like how the scalar equation is useful, and then the next video as a supplement, I'll show you examples 2 and all the way over. Okay, so here is the idea. Here is where here's where the normal also shines. If you have a direction vector, let's pretend this is the direction vector. So from 0 all the way over here, I have x minus 0 and y minus 0. Long story short, you have your direction vector right here. Let's pretend that's your direction vector. If I have my direction vector and I have my normal, you know that the angle between a direction vector and its normal, by definition, it has to be 90 degrees. Which means, what happens if I dot product two vectors in 90 degrees? The answer will automatically be 0. So the same way, whatever my direction vector is, whatever my normal is, dot product with whatever my direction vector is, you will get the same setup. Ax plus by plus c equals, or plus a constant, some number, equals 0. By a and b, it's the normal. Let me show you what that looks like, okay? This is how useful it is. I'm going to show you method 1, which is the quick way, and then method 2, which is the long way, okay? So determine a Cartesian equation, aka a scalar, equation of a line passing through 4, negative 2, and has the normal 5, 3. Okay, so what I'm looking for is something x plus something y plus something equals a 0. That's the Cartesian equation. Before any calculation, you know that 5, 3 corresponds with the coefficients because it's the normal. And so you literally just copy 5x plus 3y. It has to be. So you might be wondering, how do we get C? Just like your grade 9 exercises, all we need is a single point that lives on the line. So 5 times 4, 3 times negative 2, C equals a 0. 20 minus 6. So my C equals negative 14. So my final equation would be 5x plus 3y minus 14 equals a 0. So simple. If we didn't have this powerful knowledge, then you'd have to go about a real roundabout way. Like let's say I don't know what that is, but I just know that normal is 90 degrees to the direction vector. Okay, that's my wife. My bad. Set up a symmetric equation. All right, so let's do this. If my normal is 5, 3, I can argue that my direction vector is going to be a negative 3, 5 or a 3, negative 5. And it doesn't really matter. Okay, and because it passes through 4, 6, I can argue that my position vector is 4, negative 2. Using these two pieces, I know my line is going to be 4, negative 2 plus a parameter of negative 3, 5, which means my parametric equation is going to be x equals 4 minus 3t and y equals negative 2 plus 5t. And if I were to isolate, man, so many squigglies, if I were to isolate for t, t would be x minus 4 over negative 3. At this point, you may be too tired to write this down, but whatever. Minus 3. And here t would be y plus 2 divided by 5. And I will set these up to be equal to each other. X minus 4 minus over negative 3 equals y plus 2 over 5. Multiply both sides by 5. And multiply both sides by negative 3. Bring everything to one side. 5x plus 3y plus 6, so that's negative 14, equals a 0. And we get the same thing. Right? So, right, using our dot product, knowing that when I dot product the slope and my normal, it's going to equal a 0. Whatever my thing is, whatever, we prove through this that the coefficient of x and y will always be the normal. It's wild. It's so useful. So consider that as another sort of technique that you have. Please note, I'd like you to try exercise 2, 3, and 4 by yourself. Just know that something that I may forget to do on the video. So I need you to know that everything we're doing in 8.1 can be transposed to lines in 3D, except for scalar, except for the scalar equation. Why? I'll ask this. If I had x, y, and z, what's the normal of a line in 3D? Right? If I have, let's say this is my thing, and I have some line going through it in 3D, what's my normal? My normal could be here. My normal could be there. My normal could be there. It could be there. It could be there. So there's no such thing as a normal of a line in 3D because there's so many vectors that can spin around that it's sort of like, it's like it's like a disc or a piece of paper that was skewered by the line. There's way too many vectors. So it doesn't really work like that in 3D. In fact, it actually represents something else. So I'm going to write here, triple star, there is no scalar equation for lines in 3D. It a scalar equation with variables x, y, and z represents something else. And I sure love to keep you in suspense, right? So you'll have to wait for that. But for now, please try exercise 234 first and really do your best and before coming back to class, okay? Once again, suffer well. I know you can do it, and I hope you'll bring lots of questions for me to do on Monday. See you then.